Imagine you're standing before a mirror and in it reflects a face identical to yours, but everything is very different, even the eyes, the smile. All carry an indescribably frightening look. The universe also has such mirrors. Amid the vastness of space, there once existed two twin planets, Earth and Venus. They were born at the same time from the same cloud of cosmic dust, sharing the same size, mass, and orbit. Yet over time, one became the cradle of life, while the other turned into an eternal sea of fire. Venus is the reflection of Earth, a cosmic mirror showing that just a small difference in the eyes of nature is enough to write two opposite destinies. And even in absolute similarity, fate can still diverge into two completely different paths. But there is also something very human about it, the idea that even the star we depend on was once a piece of a family. Now we will begin the journey to explore Venus, the blazing reflection almost completely opposite to Earth. In the dark velvet of the solar system, two worlds were once alike. Earth and Venus born together from the same swirling dust carved by the same newborn sun. One turned blue its surface, breathing through oceans and rain. The other, wrapped in pale clouds, kept her face hidden. They began as twins, yet one became a cradle of life, the other a furnace of silence. Venus is almost our reflection. Her size, her density, her pull of gravity all whisper the same familiar physics. A planet nearly the same mass, the same curve, the same delicate balance of rock and metal. If you were to stand on her surface, you would feel the same weight as you do here, and yet the air would crush you in an instant. Pressure there is 90 times heavier than ours. The temperature 460 degrees Celsius enough to melt lead enough to erase every trace of water. Above the clouds shimmer with acid droplets of sulfuric rain that never touch the ground. Lightning flashes silently through the haze hidden from space by that dense eternal veil. Scientists call her the evil twin. It's a cruel nickname, but an honest one. Two planets shaped by the same rules of gravity and chemistry, yet one followed the path to paradise, the other to hell. What made them diverge? Somewhere in their early histories, one feedback loop slipped. Carbon dioxide, once balanced by oceans, began to rise unchecked. The greenhouse spiraled, the oceans boiled, the clouds thickened, and the planet sealed itself beneath its own breath. Still, the resemblance remains haunting. Venus lies close enough to be seen at dusk, shining like a drop of silver fire, beautiful, serene, and deceptive. She looks like a morning star, but she hides an inferno. If we could peel away her clouds, what stories would we find beneath that molten calm? The same physics that once gave life here might still be burning there, reshaping, rebirthing, refusing to die. And so, as we gaze at her from afar, one question remains: how alive can a dead world be? Step closer and the beauty of Venus begins to turn heavy. What looked like a soft ivory glow from space becomes a crushing weight, an atmosphere thick enough to bend metal and silence sound. Every meter of descent feels like a descent into time itself, into a past where heat and gas ruled over stone. The air there is almost pure carbon dioxide. The pressure on the surface, 92 times what you feel at sea level on Earth, is equal to being under a kilometre of ocean. If you stood there, your body would be flattened in seconds, your voice trapped in air, so dense that even echoes can barely move. The light itself seems to slow down, filtered through clouds of sulfuric acid and soot, turning the horizon into an eternal twilight of orange and gold. The ground glows faintly with heat, not from the sun but from the planet itself. At 460 degrees Celsius, it is hot enough to melt lead, zinc and tin to soften the very walls of a spacecraft. Even the strongest alloys sent by humans have lasted only a few minutes. Venera 13. One of the Soviet landers touched down in 1982. It survived for just over 2 hours, long enough to send a handful of images of broken, jagged rocks, before its circuits dissolved in the inferno. Scientists who studied those images describe a world frozen in its own fever. The stones appear scorched. The ground fractured the horizon eerily flat, as though everything had been poured, not formed. No wind moves, no dust drifts, only the heat rising endlessly like the breath of a dying giant. And yet, amid that violence, there's an elegance, a quiet order in how chemistry and physics conspire to trap a planet within itself. A world too close to the sun, too heavy to release its own air, too bright to ever cool. Venus is not cruel by choice. She is the consequence of imbalance, a reminder that nature never punishes, it simply continues. And within that continuation, the question deepens: could the same forces that burned her once have kept her alive? If Earth and Venus began as mirrors, something must have cracked that reflection. The symmetry of their birth hides a deeper divergence, one that turned an almost twin world into our most haunting opposite. For every similarity they share, mass gravity density, there is an opposite that defines their fates. Earth breathes, cycles, renews. Venus suffocates, stagnates, and seals itself within a sky of poison. The difference scientists believe lies not in where they were born, but in what each world chose to keep and what it lost. Long ago, Venus may have known oceans. Computer models suggest that for the first 2 billion years, temperatures could have been mild clouds, thin enough for sunlight to reach the surface. Water might have flowed in shallow seas, carbon could have cycled between rocks and air, and rain could have cooled her plains. If that world existed, it was fragile, perched on a delicate edge between balance and collapse. Something shifted. Perhaps the sun grew slightly brighter. Perhaps volcanic outgassing released too much carbon dioxide too quickly. Once the temperature rose just enough, the oceans began to evaporate. Water vapor, a greenhouse gas stronger than CO2, thickened the atmosphere even more. It was a runaway effect, a feedback loop without mercy. The sky closed, and the surface drowned in heat. Today, that same greenhouse still traps every ray of sunlight that reaches her clouds. Her air glows with infrared fire. The night side never cools because convection carries the heat endlessly around the globe. There is no escape, no respite, no rain. To study Venus is to look at an alternate version of ourselves, a reminder of how small the margin truly is between stability and collapse. Scientists call this the Venus syndrome, the point at which climate balance becomes irreversible. It is not just a story of another planet, but a warning written in the language of geology and loss. Venus mirrors what Earth could have been, or could still become. A twin not born evil, but transformed by its own breath. And through that mirror we see both our origin and our possible ending. For centuries, Venus was a light in our sky, not a place we could touch. It shimmered at dusk and dawn, a bright, faithful star, the first to appear, the last to fade. Ancient civilizations worshipped it as a goddess, a symbol of beauty and love. They could not have known that beneath that radiance lay a world of pressure, acid, and heat. When the age of spaceflight began, that illusion finally began to break. In the 1960s and 70s, both the United States and the Soviet Union turned their attention toward the planet that had teased humanity for millennia. It was the Soviets who succeeded first. The Venera probes became the first machines to not only reach Venus, but to survive its wrath, if only briefly. Venera 9 transmitted the first black and white images from its surface slabs of rock under a sky the colour of brass. Venera 13 and 14 followed, lasting little more than 2 hours before melting into silence. Those photos remain the only direct glimpses we have of Venus's ground. They show no rivers, no mountains of life, only fractured plains, scattered stones, and stillness so complete that it feels eternal. Each mission was both triumph and loss. Every spacecraft that landed was sacrificed, crushed, and burned, yet each returned a piece of truth. From radar echoes to chemical spectra, we began to rebuild the image of a world hidden behind its own disguise. Magellan, orbiting between 1990 and 1994, revealed the contours of continents, plains, and vast volcanic plateaus. It mapped 98% of the surface not with light, but with radio waves piercing through the haze. Venus for the first time had a face, but the deeper we looked, the more questions rose. If this world is so hostile, why does its surface look so young? If there is no tectonic life, what keeps reshaping it? And if the heart of Venus still burns, what rhythm does it follow? To search for those answers is more than science. It is reflection, a study of how fragile warmth and balance can be. Venus is not just a neighbour in space. She is the mirror by which Earth measures its own future. To study Venus is to confront a mystery wrapped in silence. Its clouds are not soft veils of vapour, but armour dense, unbroken, and blinding. From orbit, the planet looks flawless, its surface hidden beneath a milky glow. No mountain, no ocean, no shadow escapes that eternal shroud. The brightest object in the sky after the moon, and yet the one we have never truly seen. For decades, astronomers tried to pierce this cover with every tool they had. Optical telescopes saw only light reflected from the upper atmosphere. No visible trace of the ground ever reached their lenses. Through those sulfuric clouds, sunlight is scattered and refracted until it loses all direction, all memory of its origin. The entire planet becomes a mirror reflecting brilliance but concealing truth. That same mirror is deadly. It traps heat, sealing the planet in its own radiation. It also erases evidence no satellite or camera can see through it. For scientists, Venus is the ultimate paradox, the nearest world yet the most remote. What we know of its surface came not from sight, but from sound. When radio waves are sent toward the planet, they bounce back in patterns, echoes that reveal what light cannot. In the 1960s, radar became the first language through which we could see Venus. Those echoes carried contours of plains and ridges, the faint suggestion of volcanic scars. But it was not until 1990, when NASA's Magellan mission began orbiting the planet, that the veil finally began to lift. Magellan mapped nearly all of Venus using radar pulses like blind fingers tracing a face. It measured elevations, slopes, and even the texture of rocks hidden beneath the haze. And what it found challenged every assumption we held about dead worlds. Craters were few, volcanic flows stretched across continents. The planet's skin looked young, as if something or someone had recently remade it. Beneath that veil lies a restless story, one the atmosphere hides but cannot silence. To uncover it, we must listen not with eyes but with echoes, to the whispers of radar, the only sound that can reach the heart of a planet, sealed in its own storm. When light failed, sound became our vision. Radar radio waves sent from orbit, reflected and received again, turned the blindness into revelation. Through this invisible sense, Venus began to emerge one echo at a time. The Magellan spacecraft launched in 1989 was not designed for beauty. It was designed for patience. It circled the planet for 4 years, painting its surface line by line with waves instead of colour. Each signal that returned from the planet carried more than distance. It carried tone, the roughness of rock, the slope of mountains, the scatter of dust. By translating these patterns into maps, scientists created a portrait of a world no human eye could ever see. When the first global mosaics appeared, they revealed something extraordinary. Venus was not smooth, not ancient, not static. Its face was scarred by volcanoes, plains of hardened lava, and fractures that spanned thousands of kilometers. It was as if the planet had once convulsed, reshaping itself completely. Radar revealed ridges that looked like frozen waves, circular crowns larger than continents, and strange domes of flattened lava, as though mountains had melted and solidified again in slow motion. Each feature whispered of heat and motion. Each fracture spoke of forces deep below the crust. But radar is not light. It does not show colour or texture, only contrast. The images are silent abstractions, bright, where signals bounce dark where they vanish. Scientists read them like geologists of shadow, inferring what kind of surface could return such echoes. From those interpretations came our first solid idea of Venus's geography: broad lowlands covered by lava plains, uplifted highlands resembling continents, and a network of faults hinting at a dynamic interior. When Magellan finished its mission in 1994, 98% of the surface had been mapped, some at resolutions down to 100 meters. The data formed not just a map, but a paradox, a young-looking world beneath an atmosphere that should have suffocated all change. What could possibly keep such a place alive? In that paradox, radar became more than a tool. It became a voice through the storm, proving that even in silence, a planet still speaks. Before Magellan, before the radar eyes that could pierce the clouds, there were the brave machines that tried to touch the surface itself. They came from one place, the Soviet Union, and they were called Venera. Each one was a test of endurance, a sacrifice built of metal and hope. The engineers who designed them knew the odds: 90 atmospheres of pressure acid clouds and temperatures hot enough to melt solder. Still, they sent them one after another into the brightest, most hostile world in the sky. Venera 9 was the first to survive the descent in 1975. It pushed through layers of choking haze, fell for nearly an hour, and landed with a thud on a rocky plain. For 53 minutes, it transmitted the first images ever taken from the surface of another planet. What it revealed was not a landscape of fire, but of stone-broken slabs, scattered shadows, and a dim copper-coloured light filtering through the toxic air. Then came Venera 10, 13, and 14. Each landed in a different region, each living for no more than 2 hours. The cameras worked in the crushing heat, sending back photographs that blurred as their lenses slowly cracked and clouded. The ground looked solid, fractured, almost glassy in places, as though the planet had been poured, not formed. The air seemed thick enough to hold its own weight, even the horizon bent under the pressure. No wind, no sound, only a stillness that felt eternal. Those few pictures remain our only true glimpse of Venus's surface, the last eyewitness accounts before everything melts. Every image is a memory of survival, a small victory against impossible odds. Scientists still study the colour gradients, the rock shapes, the reflections of heat, looking for clues about composition erosion or hidden movement. But the images whisper the same truth again and again. Beneath that dense sky lies a planet frozen in motion, trapped mid-breath between eruption and silence. The Venera probes did not just see Venus. They proved she can still be reached, if only briefly before the heat takes everything back. The Venera images gave us glimpses but not answers. They showed what Venus looked like, not what it was doing. And so the search turned from pictures to patterns, from what the eye could see to what the planet could whisper back. Radar became the ear that listened, and through it we began to hear the slow pulse of a world that might still be alive. Each reflection that Magellan sent home contained more than shape. It carried motion, tiny shifts in brightness, and echo delay that hinted at change. Surface waves that shimmered slightly differently from pass to pass. Thermal anomalies that did not match their neighbours. They were subtle, almost lost in the noise, but they repeated, and repetition means rhythm. Some scientists began to suspect what others feared to believe. Perhaps Venus was not a fossil, but a body still breathing in heat. Yet in a world sealed beneath sulfur, and fireproof is slippery. The radar sees the skin of the planet, not the blood beneath it. The signals return cleanly from rocks, but vanish in dust, distort in heat, and shift with angle. To call those ripples activity is both bold and uncertain, and so the data remains like an echo from a cavern. Something is there, but the source is hidden. The challenge grows deeper because no spacecraft can stay. The thick air melts parachutes, the heat destroys circuits, the pressure crushes hulls. Venus resists being observed, as if guarding her secrets in layers of acid and time. We are left with glimpses through radar and spectra, fragments of heat signatures, and spectral whispers of gases that shouldn't be there. Perhaps volcanic plumes still rise and fall somewhere below, perhaps the crust still shifts slowly in the dark. The question is not only whether Venus is alive, but whether we are listening carefully enough to hear her. Every signal that bounces back through the clouds is a heartbeat in code, faint, uncertain, but undeniably there. The planet speaks through echoes, and each echo seems to say the same thing: I am still here. You just have to look differently. When the radar maps of Magellan were finally complete, they revealed a revelation disguised as simplicity. Venus beneath her clouds did not wear the face of an ancient world. Her skin was too smooth, too clean, too untouched by the scars of time. For a planet billions of years old, the count of impact craters, those universal markers of cosmic history, was shockingly low. Only about 1,000 have been identified, scattered unevenly across the surface. Compare that to Mercury or Mars, or even Earth's moon bodies pocked and cratered from eons of bombardment. Those worlds bear the signature of age, a diary of every collision written in stone. Venus, in contrast, seemed to have turned the page. Her diary was wiped almost blank. At first, scientists thought the thick atmosphere might be responsible. After all, its dense carbon dioxide envelope could easily burn or break apart smaller meteoroids before they reached the ground. But the calculations didn't fit. Objects larger than a few kilometers would still have punched through the clouds, leaving scars impossible to erase, yet they weren't there. The missing craters pointed toward a far stranger possibility: that something on Venus had erased them. The implications were staggering. Either the surface had been renewed by some slow and steady process, like a constant breath of lava resurfacing the plains, or it had been violently remade all at once in a single catastrophic episode. Whatever the mechanism, it had to be powerful enough to rewrite nearly the entire crust, smoothing away billions of years of celestial history. To planetary scientists, this made Venus feel young. Its face, measured by crater density, might be no older than 300 to 600 million years, a blink in planetary time. That youth is deceptive, though. A world can look new and still be ancient at heart. And so the question deepens: if Venus erased her surface so recently, what force acted as her hand? What breath reshaped an entire planet? Beneath her calm veil of clouds lies the paradox of youth, within age a planet that refuses to look as old as it should. and perhaps in that defiance we begin to glimpse the secret of her still beating heart. If the young surface of Venus was a puzzle, the pattern of its scars made it even stranger. Each crater that exists is a clue, a frozen impact, a timestamp of catastrophe. But on Venus, the craters are not random. They appear to have formed in a single chapter of history clustered within a narrow window of time. Unlike the Moon or Mars, which display layers of eras, Venus seems to have lived only one. This observation changed everything. On other worlds, craters overlap the old buried by the new, the story layered like sediment. On Venus, they all sit together on top, fresh and evenly distributed, as if they were written after the planet's last great cleansing. It's a pattern that points to one haunting possibility, that nearly the entire surface was wiped clean, and then sometime afterwards struck again by cosmic debris. A rebirth followed by silence. Scientists ruled out the atmosphere as the main filter. Venus's thick air can incinerate small rocks, yes, but it cannot protect against the large impactors that carve kilometre-wide scars. If those are missing, it means something far more dramatic occurred. The planet itself must have erased them. But how there are no tectonic plates to drag the crust downward, no rivers to erode, no ice to grind the surface flat? And yet the evidence of renewal is undeniable. Perhaps the heat from below melted vast regions at once, covering the land in sheets of lava that smoothed away the past. Perhaps volcanic plains flowed slowly century by century until every crater softened and vanished beneath new rock. Whichever it was, it left Venus geologically young and geologically mysterious. To planetary scientists, this quietness feels deceptive. A world that looks calm may still conceal turmoil beneath its crust. Each crater that remains is a whisper from before the change, a relic from an older world that no longer exists. And through that silence, one thought echoes: if Venus could erase her own history, once what would stop her from doing it again? The smoothness of Venus's face is not an accident. It is evidence, but evidence of what? When scientists compared its crater count and distribution with the geological records of other planets, one conclusion began to form: Venus must have renewed itself. Somehow in the last billion years, perhaps much more recently, the planet's surface was remade, erased and born again. Two families of thought soon emerged. The first argued for a slow, steady renewal, a planet that never truly rests, constantly resurfaced by local eruptions. The second envisioned something far more violent, a single global catastrophe, where the crust itself melted and refroze, leaving behind a new skin and no trace of the old one. Either way, the conclusion was the same: Venus is not as quiet as it seems. The radar data strengthened this view. Many of the plains appear remarkably uniform, as if they were poured in one immense flood of lava. Their boundaries are sharp, but their ages measured by crater density are nearly identical. That uniformity is unnatural for a planet without tectonic plates. On Earth, the crust is constantly recycled by plate motion, torn apart and pushed down in a rhythmic dance. But Venus's crust is a single locked plate. To erase itself, it must have found another way. Perhaps pressure from within accumulated until the lithosphere, the outer shell, could no longer hold. When the stress broke, molten rock surged upward in waves, flooding the surface in fire. Entire continents might have drowned in lava within a geological instant. Then the world cooled again, sealing over like a wound. The old Venus died and a new one took its place. No one knows when the last of those flows hardened, but the lack of ancient scars tells us that it wasn't too long ago. Maybe hundreds of millions of years, maybe less. And if a world could burn itself clean once, could it do so again? The question turns from history into possibility. Venus may not be dead. She may simply be sleeping between heartbeats. If Venus truly renewed herself, the agents of that transformation must still linger: the volcanoes. They are everywhere, scattered across the planet like ancient altars of fire. Some rise as isolated mountains, others form sprawling fields of lava that stretch for thousands of kilometers. In total, radar mapping from Magellan revealed more than 1,700 major volcanic structures and millions of smaller domes and vents. 3/4 of the surface is paved in basalt, frozen rivers of molten rock. On Earth, such vast plains are born from tectonic spreading and the subduction of crust. But Venus has no moving plates. Her outer shell is a single unbroken layer, a lid sealed tight over the heat below. So the energy trapped inside finds other paths, bursting upward in plumes through weaknesses in the crust. Each eruption releases not only molten rock, but also carbon dioxide, sulfur dioxide, and traces of heavy metals, gases that feed the planet's dense, poisonous air. These volcanoes are more than relics of the past. They are the most likely reason her surface looks so young. Their flows may have washed away craters, smoothed valleys, and repaved entire regions in shimmering basalt. Even now, their shapes seem too crisp, too unweathered to be ancient. Some look as though the lava cooled only yesterday. From orbit, the largest formations dominate the radar maps. There is Mart Mons, the tallest volcano on Venus, rising 8 kilometers above the plains higher than Mount Everest. Nearby lie vast volcanic plateaus crowned with strange circular structures known as coronary rings, hundreds of kilometers wide, likely formed by the upwelling and collapse of molten material beneath the crust. These features suggest that Venus is still restless, that the mantle beneath her unbroken skin continues to churn. In this realm of fire, the planet's heartbeat is written not in light, but in heat. Every mound and ridge may be a fossilized pulse of that inner rhythm, and though no human has heard it directly, the echoes of eruption remain quiet, steady, waiting to return. On Earth, mountains rise and vanish through a patient rhythm. Crustal plates drift, collide, and dive beneath one another. The motion is slow, but it is the heartbeat of our planet's renewal. Old rock sinks, new rock emerges, and in that exchange the world stays alive. But on Venus, this dance never began. There are no tectonic plates sliding past or folding under. Her crust is whole, seamless, heavy, and unyielding. For decades, this realization baffled geologists. Without tectonics, a planet's surface should age and harden its heat, trapped within its crust, frozen in place. And yet Venus is anything but geologically frozen. Her plains gleam with evidence of youth, her volcanic scars are clean and unweathered. Somewhere deep below, a different mechanism must be moving the heat. Something more primitive, perhaps. Something closer to what Earth once was before the continents learned to drift. Radar images reveal broad belts of fractures and ridges, tectonic in appearance but not in behavior. They don't mark the edges of moving plates. Instead, they are signs of expansion and compression within a single solid shell. Imagine the skin of a fruit swelling under heat, from within splitting but never breaking apart. That is how Venus releases pressure. Her lithosphere flexes, warps, and reshapes itself locally, but never enough to divide. It is a planet straining against its own armor. The consequence of this stillness is paradoxical. Without subduction, there is no recycling of crustal material, no way to bury carbon or rebuild minerals. Every gas that escapes through volcanoes stays in the air. Over time, this accumulation has suffocated the planet, trapping heat in a runaway greenhouse. What tectonics release on Earth-Venus retains every breath of its interior remains suspended in its sky. Some researchers call this state stagnant lid convection. The mantle below churns like boiling tar, but the crust above remains a single immobile raft. Pockets of magma rise and fall beneath it, heating the surface from below building pressure over eons until cracks open and massive eruptions flood the plains. It is a geological pulse, not a heartbeat, slow, sporadic, but powerful enough to rewrite continents. The absence of tectonics then is not peace. It is tension pressure gathering in silence, waiting for release. Venus may appear still, but beneath that calm mask lies a body under strain, a world breathing through fractures rather than motion. Her surface holds for now like glass over fire, but glass can bend. It can even shatter. If one day Venus were to break her silence again, the eruption would not come from a single volcano or valley. It would come from everywhere at once, the planet exhaling in molten light, reclaiming her surface in one final fiery renewal. The radar eyes of Magellan did more than map the land, they exposed a language written entirely in stone. Each curve, each ridge, each fractured ring across Venus tells a fragment of that unspoken story. To read it is to trace the movements of fire, slow and deliberate, shaping a world without sound. Venus is covered with volcanoes, but not the kind we know. Her eruptions do not carve peaks that reach for the sky. They spread outward, building wide, shallow domes that cover the land like molten seas. Where Earth's lava can be fluid and fast, Venusian lava is thick, rich in metals and silicates flowing like honey under unbearable heat. When it cools, it does not crumble into ash but freezes into smooth metallic plains. From orbit, these plains reflect radar like mirrors gleaming in monochrome. They are the fingerprints of a planet that once flowed. Among the most remarkable of these structures are the pancake domes, vast circular mounds several kilometers wide, but rarely taller than a few hundred meters. They are the quiet children of slow eruptions built layer by layer as viscous lava oozes outward and stiffens at the edges. On Earth, similar forms exist only in volcanic fields rich in silica, but even those pale in comparison to the perfection of Venus's domes. Each one is nearly symmetrical, flawless, as though shaped by an artist working in molten glass. Then come the coronae, vast circular features unlike anything else in the solar system. Some stretch for more than 1,000 kilometers, forming immense rings of fractures and ridges. They are thought to be born from plumes of magma that swell beneath the crust, pushing upward, until the surface bulges, cracks, and finally collapses under its own weight. What remains is a ringed scar, a signature of energy spent and stored again. There are hundreds of these corona scattered across Venus, some ancient, others suspiciously fresh. In many, scientists detect signs of thermal anomalies, hinting that the fires below may still flicker. Elsewhere, shield volcanoes rise like sleeping titans. Mat Mons, the tallest of them, stands over 8 kilometers high, its slopes cut by long branching channels that once carried rivers of molten rock. These channels run for hundreds of kilometers, sometimes encircling old craters, sometimes vanishing into the smoothness of the plains. Their edges remain sharp, unblurred by erosion or wind. They're too clean, too precise, too recent-looking for a world that should have been geologically silent for millions of years. Taken together, these shapes, domes, shields, and rings form a pattern. They are not scattered randomly, but evenly distributed across the planet. That uniformity suggests something profound. Venus does not release her energy through isolated volcanoes like Earth does. Instead, the whole mantle seems to pulse as one, a planet of global breath heat rising everywhere at once, pressing gently but relentlessly on the crust above. In these frozen sculptures of fire, we see a planet suspended between two states, neither dead nor fully alive. The crust is rigid, but the mantle stirs. The surface appears still, yet it whispers of movement beneath. Every pancake dome, every corona, every fracture is a fossilized heartbeat, captured mid-throb. When scientists look at the radar mosaics, they see more than geography. They see rhythm and ancient cadence written in lava, and fracture proof that Venus has not finished its story. The shapes of fire are her handwriting, and through them she tells us the same thing: in every form I once burned, I may burn again. If Venus still moves, then somewhere beneath her solid shell, something must still be stirring. The surface alone, the volcanoes, the plains, the circular scars cannot explain the planet's restless appearance. To understand the true nature of Venus, one must go deeper into the unseen, into the heat that rises from her heart. Every planet carries an internal rhythm, a pulse set at birth by the energy trapped within it. In the beginning, that heat came from the violence of creation, from impacts from compression, from the lingering fires of radioactive decay. On Earth, the heat found balance. It escapes through spreading ridges, through the slow drift of continents, through volcanoes that breathe and release. It is a system of exhalation, constant, stable, alive. But Venus, sealed beneath her own unbroken crust, cannot breathe in the same way. Her lid is thick, 30 to 50 kilometers of dense rock, without the fractures and seams that make Earth flexible. The energy within her mantle does not flow freely. It swells and churns, trapped until the pressure becomes unbearable. Imagine a planet whose heartbeat is muffled, still pounding, but heard only through vibration. Scientists call this state stagnant lid convection. It is both a diagnosis and a mystery. The mantle of Venus still convects, rising in slow plumes of molten rock, falling again as it cools, repeating over millions of years. But the crust above it remains mostly solid, bending only when the pressure grows too great. In those moments, the heat bursts upward through cracks, flooding the surface with new lava, not in constant motion, like Earth's tectonics, but in rare global spasms of renewal. Each eruption might last tens of thousands of years, followed by hundreds of millions of silence. Beneath this system, the core itself remains enigmatic. It is thought to be large, about 3,000 kilometers in radius, rich in iron and nickel, not unlike Earth's. But there is no magnetic field to mark its presence. Unlike Earth, Venus lacks a global magnetosphere, that invisible shield, born from the spinning of molten metal around a solid center. If the core of Venus is molten, it must not be moving fast enough. If it is solid, then the planet has lost one of the engines that drives renewal. Either way, the silence of its magnetic field tells us something profound. Venus's heart still beats, but weakly, like an echo remembered rather than felt. Still heat escapes. Even a trapped world cannot hold everything in forever. Infrared measurements show subtle variations in surface temperature patches that appear slightly warmer than they should be, suggesting that magma may lie close beneath. Some coronae still radiate heat higher than their surroundings. Some rift zones emit strange chemical signatures in the upper atmosphere. Sulfur dioxide, a gas easily broken down by sunlight, sometimes spikes in concentration, then fades, then rises again. It is as if something below occasionally exhales, releasing brief gusts of volcanic breath before falling quiet once more. These pulses are not random. They might be the planetary equivalent of size slow releases of pressure as the mantle adjusts. On Earth, such fluctuations would mean active volcanism. On Venus, they are the only signs of motion left for us to read. Radar comparisons decades apart even suggest changes in certain volcanic vents, small differences in slope and brightness that may mark new flows of lava. Between 1990 and 1992, Magellan may have caught one such moment. A volcano subtly reshaped its vent, widened its surroundings, altered by what looked like fresh, cooling rock. If confirmed, it would mean that Venus erupted within our lifetime. But the pulse of Venus is more than a measure of heat. It is a mirror of isolation, a reminder that even a planet can suffocate under its own creation. Trapped heat becomes identity. Trapped gases become fate. Each wave of magma that rises, each fracture that opens, is a symptom of the same condition, a world that never learned to let go. Scientists build models to estimate how this energy cycles. Some suggest that Venus alternates between two modes, a long quiet phase where heat accumulates followed by a catastrophic release that renews the crust. Others believe the process is more continuous local bursts and flows that together maintain the illusion of youth. Whichever model proves true, both paint the same picture. Venus is dynamic, but her dynamics are hidden from sight, concealed by her thick, brilliant atmosphere. If we could look beneath that atmosphere, not with radar, not with radio, but with vision, we might see continents of slow fire, red and molten under a stone sky. We might see valleys where magma drips like blood, cooling into glass, reforming again centuries later. We might see the planet breathing painfully heavily, but breathing nonetheless. The absence of tectonics is not death, it is restraint. The absence of a magnetic field is not silence, it is waiting. Venus is not a corpse, but a patient heat still surging through her veins, waiting for the crust to crack, for the fire to speak again. And though her pulse is buried deep, we can sense it through radar echoes, through infrared signatures, through faint shifting clouds of sulfur and light. They are tremors of life within stillness, proof that even under a sealed sky motion survives. Venus hides her heartbeat well, but the universe is patient. Eventually, all that is trapped finds its way out. When that happens again, when the next great eruption swells from her mantle, it will not be small. It will not be gentle. The entire planet will exhale, and the young surface we now see will vanish beneath another tide of molten rock. Venus will shed her skin once more, just as she has before. And as we watch her from our cool blue distance, we will know the quiet was never peace. It was only the deep inhalation of a planet preparing to breathe fire again. If every planet carries a secret, Venus's is her heat, the invisible force that both sustains and destroys her. It is the pulse that never ceases, the quiet architect of her surface, and the reason she appears young when she should be ancient. To understand why the planet's crust looks freshly poured, why the scars of impact have vanished, we must begin not with the rocks we see, but with the energy beneath them. Every planet starts with a reservoir of heat born from the chaos of its creation. Billions of years ago, when dust and gas condensed into worlds, collisions were constant, each impact releasing kinetic fury that melted stone into oceans of magma. That initial fire faded, but it never died. In Venus, as in Earth, the heart still burns from within. The main source of that enduring heat is radioactive decay, the slow breakdown of elements like uranium, thorium and potassium embedded deep in the mantle. Each atom that splits releases energy, and over millions of years that energy builds. On Earth, this heat is constantly vented through tectonic motion and volcanic breathing, a dynamic balance between generation and release. But on Venus, the crust is too rigid, the skin too thick. There are no tectonic plates to carry warmth upward, no oceans to draw heat away, no circulation of water to moderate the system. The result is accumulation energy, trapped unable to leave simmering under a lid of rock and carbon dioxide. Geophysicists describe it as thermal isolation. It is the ultimate paradox, a world next door to the Sun whose surface burns at 460 degrees, and yet whose core still cooks from within. The heat that should have escaped long ago instead rebounds, slowly saturating the mantle, softening its interior, weakening its crust. In time, that energy must go somewhere. And so two competing visions of Venus's evolution were born, two scenarios of renewal that could explain her deceptive youth. The first is the catastrophic model, a world that holds its heat too long until the build-up becomes unbearable. For hundreds of millions of years, the interior pressure rises silently. The crust, though unbroken, begins to fracture and stretch. Magma pools beneath the lithosphere like breath under glass, searching for escape. Then, in a geological instant, the tension gives way. The crust buckles, the mantle surges upward, and Venus convulses. In this view, the planet does not vent her energy gently but violently, an episode of global resurfacing, where fire sweeps across nearly every continent, burying the old landscape under new lava. Evidence for such a catastrophe lies in the near-uniform age of the surface. Unlike Earth, where mountains, basins and oceans record billions of years of change, Venus's topography tells a simpler story. One surface, one era, one scarless face. The craters are few, their distribution nearly random, as though they were laid down after a single planet-wide cleansing. Computer simulations of this process show that if Venus's interior heat built up faster than it could escape, the crust could melt from below, collapsing in sheets that reseal within a few 100,000 years. To a geologist, that's the blink of an eye, the rebirth of a world. But others argue for a more gradual story, one less apocalyptic but no less remarkable. They propose that the planet's renewal was not a single event but a drawn-out cycle, a slow-rolling wave of volcanism spreading across eons. In this gradual model, the heat escapes not all at once, but through scattered eruptions and regional floods of lava occurring in clusters across the globe. Each eruption smooths a patch of crust, adds a layer of new basalt, and slightly resets the surface's age. Over hundreds of millions of years, the planet effectively repaves itself, not with one global convulsion, but with a patient, rhythmic breathing of fire. The difference between the two models, catastrophic or gradual, is more than a matter of timing. It changes everything we think we know about how planets evolve. A catastrophic resurfacing implies a world of extremes where energy builds in silence and is released in violence. A gradual renewal suggests an active, enduring interior where volcanic systems have persisted far longer than we imagined. In both, Venus becomes a world of heat, but one expresses it in pulses, the other in a continuous glow. To decide between them, scientists turn again to data radar spectral readings, infrared imaging. The smooth plains and circular corona hint at a mix of both behaviours, global events that may have been punctuated by smaller lingering eruptions. If so, Venus may have entered a pattern of thermal cycles, long dormancy, followed by upheaval, followed again by calm. Each phase could last hundreds of millions of years, a pendulum swinging between fire and stillness. Deep inside that rhythm might still be playing. Measurements of gravity and density suggest that the mantle remains partially molten, and that plumes of rising magma still form beneath the crust. They do not break through often, but when they do, they could renew entire regions in bursts of activity, invisible through the thick clouds. The atmosphere's occasional spikes of sulfur dioxide could be the faint chemical traces of those eruptions, ghostly fingerprints of an ongoing cycle we can't yet see. The catastrophic and gradual models may not be opposites after all. They may be chapters in the same repeating story. Venus builds heat, releases it, then builds again. The question is not whether she has resurfaced, but whether the next renewal has already begun. From this perspective, the planet's smooth plains are not the ashes of a dead world, but the calm between storms. The stillness is deceptive. Even now, the heat within continues to climb generation by generation, atom by atom. At some point, perhaps in another 100 million years, perhaps sooner, the balance will tip again. The crust will fracture, magma will rise, and the face of Venus will change once more. To watch her is to witness a paradox of time, a planet frozen on the outside yet alive inside, pulsing with energy it cannot express. Venus reminds us that stillness does not mean rest, it means waiting. Waiting for the inevitable moment when the trapped heat becomes motion again, when silence becomes eruption, when the planet exhales. And when that moment comes, the transformation will not be gentle, it will be complete. The planet that looks timeless now will again shed her surface like skin, and for a brief fiery instant she will be reborn. That is her cycle, her rhythm, her nature, a world of fire constrained by stone forever repeating the same ancient breath, to burn, to cool, to burn again. To imagine Venus remaking herself in fire is to picture a planet-sized paradox, a world that looks utterly still, yet carries the memory of a storm so immense that it erased its own past. The Magellan radar maps reveal more than shapes and ridges. They reveal the aftermath of something total, a silence that follows an event beyond comprehension. The surface is smooth, the craters scarce, the fractures widespread but evenly distributed. Every feature seems to belong to the same era, as though all of Venus were reset at once. For a planet to do that, something extraordinary must have happened, not a gentle geological process, but an overwhelming event that melted, buried and rebuilt almost everything. This is the catastrophic resurfacing hypothesis, the idea that Venus's entire outer shell once gave way under the pressure of its own heat. Imagine it a world whose interior grows restless, the mantle swelling like a tide trapped under stone. For millions of years, the pressure builds magma accumulating in vast unseen chambers, the crust bending, cracking, but refusing to open. Then, at some breaking point, the strength of that shell fails. Molten rock, long suppressed, bursts upward in torrents. Volcanoes erupt not singly, but in unison. Lava floods the lowlands, drowning craters and mountains alike. The air fills with gases, carbon dioxide, sulfur dioxide, thickening the already suffocating atmosphere. The entire surface becomes a furnace glowing from horizon to horizon. It is not a single eruption, but billions merging into one, a world turned inside out. When the heat finally subsides and the lava cools, the planet is reborn. The old craters are gone, the ridges softened, the scars erased. In their place stretch smooth plains of basalt, new dark, reflective, unmarred by time. What remains is a snapshot of youth frozen just after the fire. That is how Venus looks today. This theory, first proposed in the 1990s after Magellan's mission, explains many of the planet's peculiarities. The consistent crater ages the absence of tectonic layering. The vast, uniform lava fields all fit a scenario of near-simultaneous resurfacing. It also fits the thermal logic of a stagnant lid planet. Without tectonic motion, heat accumulates slowly until it finds catastrophic release. Venus, in this view, lives not by gentle cycles, but by convulsions, eons of stillness, punctuated by world-consuming bursts. Yet the catastrophic model raises as many questions as it answers. If the last great eruption ended 300 to 500 million years ago, what has happened since? If Venus purged her heat so completely, how could she remain so hot today? Shouldn't she have cooled? Shouldn't the fire have faded? The answer scientists suspect may lie in what happened after the cataclysm. Once the surface hardened again, the same insulation that caused the eruption began trapping heat anew. Venus may exist in a thermal loop. Each global convulsion resets the crust, sealing in the heat until the process repeats. The planet cools on the outside but continues to warm within, setting the stage for the next great release. The calm that follows each catastrophe is therefore an illusion, not the end of activity, but the start of another build-up. Evidence of that continuing restlessness can be seen in the fractures and ridges that cross the plains. They are not chaotic. They form long linear patterns, sometimes stretching for thousands of kilometers, sometimes looping around vast coronae. These networks record stress, the slow expansion and contraction of a crust still responding to inner motion. In some areas, the cracks appear fresh, cutting across older lava flows. In others, they seem softened by time. This layering suggests that even after the great resurfacing, smaller eruptions and deformations have continued to reshape the planet, albeit less dramatically. The coronae themselves support this idea. Many of them show signs of partial collapse and refilling, as though the plumes beneath them are still active. The largest, such as Artemis corona, spans more than 2,000 kilometers and displays concentric fractures that appear to have formed in stages. Infrared studies indicate that some coronae still emit slightly higher heat than their surroundings, hinting that magma may lie close beneath the crust. If so, Venus's catastrophe may not be a single event frozen in history, but an ongoing phenomenon, a planet forever oscillating between fire and stillness. The atmosphere too carries the fingerprints of that hidden activity. Periodic spikes of sulfur dioxide detected by orbiters and ground-based telescopes suggest that volcanic gases are still escaping. Since the sunlight in Venus's upper atmosphere breaks sulfur dioxide down quickly, these spikes cannot persist long, unless new material is being supplied from below. That pattern of chemical variation fits a planet that occasionally exhales not constantly, but often enough to remind us it's not dead. Still, some researchers remain cautious. They argue that the catastrophic model paints too simple a picture that Venus's resurfacing may have been more complex, a patchwork of overlapping flows rather than a single world-ending event. They point to subtle variations in crater density suggesting that some regions are slightly older or younger than others. This could mean that global resurfacing was a process that swept the planet gradually, perhaps in waves over tens of millions of years. The difference between catastrophe and slow renewal might only be one of tempo. Yet even if the process unfolded over millions of years in geological terms, it would still be sudden, an entire planet transformed within the blink of deep time. Whether in one catastrophic surge or in a prolonged cascade, the outcome is the same: an almost completely new surface, less than 1 billion years old, covering a body billions of years ancient. The calm that followed the Venus we see today is the silence after the storm. Her plains have cooled, her volcanoes rest, her clouds thicken again. But the memory of that eruption lingers in the chemistry of her atmosphere, in the cracked patterns beneath her crust, in the faint warmth that refuses to fade. Venus may have buried her past, but she has not buried her fire. From a distance she shines softly in the morning sky, her light serene and steady. But behind that serenity lies violence beyond imagining a planet that destroyed itself to begin again. If the catastrophic model is true, then the surface of Venus is not ancient ground, but the crust of a phoenix cooled from the last cycle of its own immolation. And if history repeats itself as the model suggests, the next rebirth is inevitable. The question is not if Venus will erupt again, but when. For now, she sleeps her mantle stirring in secret, her heat building beneath a lid of stone. The calm is deceptive, the peace temporary. In the long quiet rhythm of planetary time, her next fire is already on its way, hidden in the depths, waiting for the moment when the planet exhales once more, and the silence of ages turns again to flame. Not every scientist believes in catastrophe. There is another school of thought, quieter, slower, and perhaps more haunting, that sees Venus not as a planet reborn in an instant of fire, but as one that has been remaking itself for hundreds of millions of years, grain by grain, flow by flow. This is the gradual renewal hypothesis, the vision of a world that never stopped moving, never stopped changing, only learned to hide its motion behind a curtain of cloud and time. To those who support this idea, the smoothness of Venus's surface does not demand a single global catastrophe. It could instead be the sum of countless local events, steady lava flows, intermittent eruptions, subtle uplifts and collapses. A planet that, though sealed and stagnant, still finds ways to release its pressure in fragments. Over eons, those fragments accumulate until the old crust is slowly replaced layer upon layer by new rock. Not a phoenix rising from its ashes, but a slow metamorphosis, a stone butterfly taking centuries to emerge. The foundation for this view comes again from the Magellan radar maps. While the surface appears uniformly young, closer analysis reveals subtle differences in reflectivity and crater degradation. Certain regions, especially the vast volcanic plains, look only a few 100 million years old. Others, particularly the highlands and corona fields, seem slightly older. The variation is small, but it suggests a temporal gradient, not a single sweeping event, but a planet that renews itself unevenly, like ice melting from the edges inward. If Venus is truly resurfacing in this slow, distributed way, then her volcanoes are not relics but participants. Each one contributes to the process, erupting now and then, spreading lava that repaves its surroundings. Over millions of years, their combined activity could explain the scarcity of impact craters without invoking a single apocalypse. The evidence lies in the morphology of the flow's narrow branching channels that resemble rivers of rock frozen midstream. Some flows extend for hundreds of kilometers, overlapping older ones like brushstrokes on a canvas. Each new eruption erases what came before, not through violence, but through persistence. Infrared data from orbiting probes has strengthened this hypothesis. Certain areas, particularly near large volcanoes like Ozimons and Martmons, emit more heat than others, not much but enough to be noticed. The variations are too localized to represent the aftermath of a global flood of lava. Instead, they point to pockets of residual warmth, places where magma still lingers beneath the surface or has erupted in the not-so-distant past. These hotspots, if confirmed, would mean that Venus is still geologically active today, not explosively but quietly in a slow planetary simmer. The gradual model also explains why Venus's atmosphere remains rich in volcanic gases. Sulfur dioxide, carbon dioxide, and trace metals should have long been stabilized if the planet were truly dormant. Yet their levels fluctuate and some chemical signatures appear inconsistent with a static world. It is as if small vents across the surface continue to exhale their emissions, blending invisibly into the thick air. If each of these vents represents a minor eruption, a release of trapped heat and gas, then Venus's face is in constant subtle motion. To test this, scientists have run thermal evolution simulations. In these models, the mantle of Venus behaves like a vast ocean of viscous rock. Convection cells rise and fall, delivering heat to the base of the crust in shifting patterns. Where the heat concentrates, the crust softens, cracks, and melts. Lava rises, cools, and spreads while the surrounding terrain remains untouched. Then over time, the focus of activity shifts elsewhere, creating a mosaic of resurfaced patches rather than a single uniform layer. The end result looks much like what Magellan saw: smooth plains interrupted by older ridges and folds with no clear boundary between them. In this vision, Venus is not a planet that dies and is reborn, but one that breathes slowly, painfully slowly through its own crust. The entire surface becomes a kind of thermal skin, expanding and contracting in long rhythmic cycles. A volcanic field here, a plain there, an eruption that lasts 1,000 years, followed by silence. Generation by generation, the old world sinks under the new until after hundreds of millions of years, every piece of the surface has been replaced. It is not a single act of renewal, but an eternal one. This gradual renewal model has deep implications for planetary science. If true, it means that Venus's interior remains active, capable of sustaining convection for billions of years, without the need for tectonic motion. It would make Venus not a failed Earth, but a different kind of success, a world that found its own path to evolution. It would also suggest that other rocky planets without plate tectonics, like many of the exoplanets we've begun to discover, might share a similar hidden dynamism. Beneath calm surfaces, they too could be alive in slow motion. Still, the model faces challenges. The precise rates of resurfacing are hard to determine. The variations in crater age are subtle, often within the margin of error. Some scientists argue that the apparent heat anomalies could be explained by atmospheric variations rather than true volcanic activity. Without direct observation, a camera close enough to watch a flow in real time, the debate remains open. And yet, even with its uncertainties, the gradual model carries a certain poetry. It envisions Venus as a planet in transition, neither dead nor reborn, but perpetually renewing herself through patience rather than power. Her story becomes one not of destruction but of endurance. Instead of a single apocalyptic outburst, she reshapes herself quietly, the way a glacier reshapes a valley, not through violence but through time. When viewed through this lens, the smoothness of Venus's plains becomes something sacred, not erased but rewritten. Every basalt field, every dome and ridge is a trace of the planet's long meditation on heat and motion. Venus does not rage, she endures. She moves with the pace of continents, exhales with the rhythm of centuries, and hides her transformation behind clouds that never part. Perhaps that is the real nature of her mystery. The fire of Venus is not a spectacle, but a hum beneath the noise, a warmth that persists long after the surface cools. If the catastrophic model speaks of rebirth, the gradual model speaks of continuity of a heartbeat, so slow we can only sense it through echoes. And maybe in the end, both stories are true. Perhaps Venus once burned in a single global fever, and now heals in quiet stages. Perhaps the last eruption was not the end of her fire, but the beginning of her recovery. A world that burned itself clean, learning at last how to breathe again, not in violence but in stillness. For all her heat and silence, Venus may yet be alive, not as a flame but as an ember. A planet whispering its renewal across the ages, not with noise but with endurance. Not through catastrophe, but through the slow, invisible artistry of time. If there is truth in both visions, the catastrophic and the gradual, then Venus exists somewhere between them. Not wholly a planet of disaster, not wholly one of patience, but a world that breathes in rhythms too vast for our senses to follow. Between fire and time, she lives in cycles: stillness, pressure, release, renewal, silence. Each phase erases the last. Each silence hides the next eruption. In the Magellan images, the record of this dual life is written plainly, though few noticed it at first. The surface is neither uniform nor random. It bears the marks of both continuity and violence, planes that stretch endlessly, yet crossed by fractures that twist and intersect like veins under a scar. Some regions appear untouched for eons, others show evidence of recent upheaval. The planet's skin is both old and young, as if frozen mid-transformation. To scientists, this mosaic is the signature of an unfinished world, a planet that never found equilibrium. Venus is not static, but she's not stable either. Her crust hardens, cracks, melts, reforms, then hardens again. Each stage gives birth to the next. This is not balance, it is recurrence, a restless geology that mimics life itself, breathing and resetting, burning and cooling. The tension between these two forces, the slow and the sudden, defines her. It is possible that Venus shifts between them over time. For long stretches she may operate under the gradual model, venting heat through scattered eruptions and localized flows. But as the crust thickens and the pressure grows, the system slips toward instability. Eventually a threshold is reached and the planet's internal rhythm collapses into chaos. In that moment, Venus crosses from calm to cataclysm. Her lid fractures, her mantle explodes upward. What was slow becomes sudden. What was patient becomes unstoppable. This cycle may have repeated more than once. Each resurfacing resets the clock, sealing in new layers of heat and altering the planet's chemistry. Each renewal begins with promise, then ends in suffocation. After the last great convulsion, perhaps 300 to 600 million years ago, Venus entered her current state, a planet recovering from its own fever, trapped again under its carbon dioxide veil, rebuilding the pressure for the next upheaval. Even her atmosphere bears witness to this unending loop. Thick and golden, it is a mirror of her past fires. Every molecule of carbon dioxide was once a breath from a volcano, every droplet of sulfuric acid once part of a deeper storm. When we look at her clouds, we're seeing her geology suspended in air, her crust turned to vapor, her mantle condensed into mist. The entire planet is caught in its own exhalation. But within that heat lies a paradox. Venus's temperature has been stable, stably extreme for millions of years. The runaway greenhouse, though catastrophic to life, may also regulate her internal energy. The dense air acts as a thermal blanket, slowing the cooling of the surface and feeding the mantle's heat from above. It is a feedback loop. The hotter she gets, the thicker her atmosphere grows. The thicker it grows, the more heat it traps. And the more heat it traps, the more the interior strains beneath the pressure. Venus is self-sustaining, but only in torment. To planetary scientists, this balance between fire and stasis is both terrifying and beautiful. It represents a kind of natural perfection, a planet perpetually on the edge, always accumulating energy but never allowed to die. If Earth is the embodiment of change through movement, Venus is change through endurance. Where we drift, she endures. Where we fracture, she compresses. Both are alive, but in opposite ways, and yet her story is not finished. Beneath the basalt plains and ancient Cronea, something still stirs. The radar data hints at shifting landforms, vents that seem to widen, domes that appear to slump or grow between observations. Infrared scans show subtle flickers of warmth too persistent to be illusion. Even the upper atmosphere, turbulent and thick with acid clouds, carries traces of volcanic gases that should have decayed centuries ago. All of it suggests that the cycle continues slowly, invisibly, but inevitably. The next phase of renewal will not arrive in a single eruption or a global flood of lava. It will begin with a murmur. Pressure will build in silence. Faults will stretch and deepen. The crust will bend, forming rifts where light never touches. For centuries the change will be imperceptible, until one day a chain of eruptions connects across continents, and the quiet planet becomes a sea of molten glow once more. Then the balance will reset. The old surface will vanish beneath the new. The atmosphere will thicken again, the air will shimmer with fire, and the slow cycle will start anew. If this is true, then Venus is a planet caught in geological memory, a world that repeats itself because it cannot evolve past its own design. It is both alive and trapped, eternal and incomplete. Every resurfacing gives her another chance, but also seals her fate a little deeper. In this way, she resembles a heart that beats not to live, but to remember. To look at Venus, then, is to see the tension between destruction and persistence. She reminds us that time on a planetary scale is not linear. It folds back upon itself, layering one epoch over another, erasing and rewriting without end. In every sense, Venus is still writing her story not in ink or fire, but in temperature pressure, and the slow geometry of motion. Future missions will search for the traces of that next chapter. NASA's Veritas mission will map her surface again, its radar sharper than Magellan's by orders of magnitude, capable of detecting changes mere meters wide. The Da Vinci probe will descend through her atmosphere, measuring gases that may carry the fingerprints of ongoing volcanism. Together they may answer the question that lingers above all others: is Venus still alive? But perhaps alive is the wrong word. Life as we know it breathes in rhythm, evolves and adapts. Venus does not evolve, she repeats. She is the archetype of planetary memory, locked in an eternal recurrence of fire and stillness. Her calm is not peace, her silence not death. They are the pauses between pulses, the moments when energy gathers before the next transformation. In the mirror of that endless cycle, we can glimpse something about ourselves. We too are creatures of renewal, of collapse and rebuilding, of destruction and creation. Our planet cools and shifts and heals through motion. Venus does the same through endurance. Both are ways of surviving, and both come at a cost. Between fire and time, Venus stands as a reminder that even the most violent transformations can be cyclical, that sometimes to stay alive, a world must burn and rebuild again and again. And if we could listen closely enough beyond the static of her clouds and the pressure of her air, perhaps we would hear it, the faint rhythmic pulse of a planet that refuses to end. The question of whether Venus is still alive is no longer a matter of poetry. It is a scientific pursuit, one conducted through the faintest signatures of heat and motion. In the last few decades, every new observation, every glimmer of data has been another heartbeat detected through layers of cloud and time. The evidence is fragile, indirect, yet it builds like a rhythm, small pulses of warmth, subtle shifts in surface brightness, transient gases that should not exist. Together they tell a story that is as quiet as it is astonishing, the whisper of heat from a world we once thought long dead. It began with Venera Express, the European Space Agency's orbiter that studied Venus from 2006 to 2014. Using its infrared spectrometer, scientists measured the planet's thermal emissions, scanning the shrouded surface through narrow windows in the atmosphere where heat could escape. What they found were anomalies, regions slightly warmer than expected clustered near volcanic highlands, such as Matmons, Ozomons and Sapasmons. The temperature differences were small, only a few degrees, but consistent enough to demand attention. Some patches glowed more brightly in infrared over time, suggesting that they were not static, that the planet's skin was changing even subtly before our eyes. The interpretation was bold but tantalizing. Perhaps these were areas of recent lava flow still radiating the leftover heat of eruption. Or perhaps they were vents fractures where gases and warmth seeped upward from the mantle. In either case, the implication was profound. Venus was not a fossilized world, but one that still exhaled. Then came another clue hidden in the chemistry of her sky. Venus's thick atmosphere is dominated by carbon dioxide, with clouds of sulfuric acid drifting at high altitude. Yet among these constant components, a variable pattern began to emerge. Orbiters and Earth-based telescopes detected fluctuations in sulfur dioxide concentration, sharp spikes followed by steady declines. Because sunlight breaks down sulfur dioxide within days, its presence in the upper atmosphere implies a fresh supply, and the only known source capable of replenishing it is volcanic activity. If sulfur dioxide were a voice, Venus would be whispering through it, faintly, irregularly, but undeniably. Each surge could mark a venting event, a plume of gas rising from deep fissures to the clouds above. Some scientists likened it to a planetary sigh, the slow release of pressure from within. Others remained cautious, suggesting that winds or atmospheric circulation could mimic such effects. But even they conceded that the pattern was too precise, too recurring to be pure coincidence. Then in 2023 came a discovery that turned speculation into something closer to evidence. By reanalyzing Magellan radar images taken 3 decades earlier, researchers identified a striking change near Matmons. Between 1990 and 1992, one volcanic vent appeared to have altered in shape and reflectivity, expanding slightly, and surrounded by what looked like a newly cooled flow of lava. It was not a vague anomaly, but a measurable transformation. If correct, it would mean that Venus experienced an eruption within the last 30 years, a geological moment so recent it fits within a single human lifetime. The implications rippled across the planetary science community. For decades, Venus had been labelled a dead twin, a world that burned itself out eons ago. But this new evidence suggested something different, that beneath her clouds she still stirs. The world once thought extinct is in truth only sleeping. Other missions have begun to refine this picture. NASA's infrared telescope facility in Hawaii has recorded subtle brightness changes in specific thermal wavelengths corresponding to volcanic regions mapped by radar. These changes are small fractions of a percent, but they persist over time following the same coordinates where earlier satellites had detected heat anomalies. No weather pattern can explain them, only geology can. Something beneath the crust is still feeding energy upward. The whisper of heat becomes clearer when seen alongside Venus's topography. Her volcanic structures are not random, they cluster in regions where mantle plumes are likely rising. The great coronal circular ridges hundreds of kilometers wide often overlap with the infrared hotspots. Some models predict that these areas are still buoyant, their underlying magma chambers slowly pressing against the crust. If the pressure continues to rise, minor eruptions could occur every few thousand years invisible beneath the clouds, but leaving thermal traces that our instruments can now detect. Even the planet's rotation hints at motion. Precise radar measurements show that Venus's day length varies slightly, sometimes by minutes, sometimes by seconds over long intervals. One possible cause is the exchange of angular momentum between atmosphere and crust. Another, more provocative, is the redistribution of mass below the surface mantle, plumes shifting flows of magma adjusting the balance of the planet. In that case, the very turning of Venus might be subtly influenced by her hidden internal dynamics. If so, then her heat is not just a residue of the past, it is an active force shaping her still. The warmth that radiates through her clouds today may come from eruptions that occurred centuries ago, or ones that are happening even now silently beneath her shroud of acid mist. To detect such faint whispers is to stretch the limits of our technology and imagination. No probe has survived on the surface for more than 2 hours. The Venera landers melted in place, their cameras clouding with heat, their circuits dissolving in the acid-laden air. And yet even from orbit the signs persist, small, consistent, cumulative. Venus is speaking through the language of energy. The challenge lies not in hearing her, but in understanding what she says. In the coming years, 2 missions, Da Vinci and Veritas, will attempt to listen more closely. Da Vinci will plunge through the atmosphere, analysing gases as it descends, searching for isotopic fingerprints that can distinguish ancient air from newly released volcanic breath. Veritas, orbiting above, will map the surface with radar finer than ever before, capable of spotting changes mere meters wide. Together they may confirm what decades of inference have only suggested, that Venus still moves, still exhales, still remakes herself from within. If they succeed, we will have to rethink not only the planet's history but its meaning. Venus would no longer be the cautionary tale of a world gone wrong, a vision of what happens when climate and geology devour themselves, but something more complex. She would be proof that even in isolation, a planet can sustain its own rhythm. That silence does not mean death. That heat hidden and restrained is still a form of life. When we look at her from Earth, bright in the twilight sky, serene, eternal, we see only reflection. But behind that glow lies movement. Lava cooling beneath clouds, gas rising in invisible plumes, a slow, ancient heartbeat pulsing through a crust of stone and flame. It is faint, yes, but it endures. And perhaps that is the greatest revelation of all, that in the vast silence of the solar system, even the quietest planet still finds a way to speak. Venus speaks in warmth. She speaks in chemical breath. She speaks in subtle change and unbroken patience. And through her the universe reminds us nothing truly stands still. Every world, no matter how quiet, still burns somewhere beneath its surface, softly, stubbornly, beautifully. There is something deeply human about our need to prove that Venus still breathes. For centuries we have gazed at her, the morning star, the evening light, and imagined her alive, a sister to our Earth wrapped in cloud and mystery. And yet, for all our instruments and equations, for all our radar maps and spectral charts, we have never truly seen her move. We have seen the traces, yes, heat signatures, chemical hints, surface changes, but not the act itself. What scientists long for now is proof in motion, an image, a signal, a flicker of transformation caught in the act, undeniable and alive. To catch Venus breathing is both a technical challenge and an act of patience. Her atmosphere conceals everything. The clouds, dense with carbon dioxide and sulfuric acid, are a million veils thick, each scattering light, each reflecting radar, each distorting what lies below. A camera cannot see through them. Even radar, that most persistent of sensors, returns echoes blurred by heat and motion. The data must be filtered, modelled, interpreted, guessed, and in those guesses somewhere a living world might be hiding. The journey to find movement began with the Magellan mission in the 1990s, when radar first mapped almost the entire surface. At that time, the instruments had no way to detect change. They were meant to reveal shape, not time. But decades later, scientists re-examined that data and noticed something remarkable. A small volcanic vent near Mount Mons had changed. Its rim had collapsed inward, its interior had darkened, and the surrounding plain showed the signature of fresh, cooled lava. Two images taken 2 years apart suddenly formed a before and after. Between them, Venus had shifted, not metaphorically, but physically. It was the closest thing yet to a photograph of the planet breathing. This revelation triggered a revolution in how researchers think about Venus. If change could be seen across just 2 years of Magellan data, what else might be happening right now hidden in the clouds? Could we design instruments capable of catching it in real time, not through inference but direct observation? That question became the heartbeat of a new generation of missions. NASA's Veritas Venus Emissivity Radio Science INSAR topography and spectroscopy is one of them. Set to launch in the early 2030s, it will orbit Venus with radar sharper than any before a synthetic aperture radar capable of resolving features just a few meters across. Its design allows for interferometric comparison. By mapping the same area repeatedly, Veritas can detect changes in elevation as small as 5 millimeters. That precision could reveal the swelling of ground before an eruption, or the collapse of a vent afterward. It could measure not just the scars of volcanism, but the motion itself, the literal rising and falling of the planet's skin. The mission spectrometers will also map infrared emissions with unprecedented clarity, tracing heat anomalies across time. If a region warms, then cools, if gases shift in concentration, Veritas will know. It will in essence watch Venus breathe. For the first time, we may witness an active planet renewing itself frame by frame, as if time itself were unfolding before us. In parallel, NASA's Da Vinci mission will do what no human-made object has attempted since the Soviet Venera probes: descend through the atmosphere layer by layer and taste the air directly. It will measure ratios of noble gases and isotopes, fingerprints of geological processes that cannot be faked. A spike in specific isotopes, especially those associated with sulfur and oxygen, could confirm that volcanic gases are still being released today. If Veritas watches the surface, Da Vinci will listen to the breath. Together they form the most intimate observation of another planet in human history. But catching motion on Venus is not merely about detecting eruptions. It is about understanding her internal rhythm, her pulse. Beneath the surface, computer models suggest convection cells rising from the mantle like bubbles in a deep cauldron. These plumes of molten rock push upward, deforming the crust in slow, imperceptible waves. If we could see through the rock, we would witness continents subtly heaving, fields of basalt tilting by fractions of a degree, the slow mechanics of planetary respiration. With radar this sensitive, we might finally measure it. Even small shifts in Venus's rotation could become evidence of motion. Astronomers have noticed that her day length changes slightly between observations, by minutes, then by seconds. Some attribute it to atmospheric drag. Others suspect movement within the planet itself, as if magma flows and mantle tides subtly redistribute mass. If so, the planet's heartbeat is not confined to its crust. It reverberates through every layer, from the glowing core to the acid clouds above. What would it mean philosophically to capture such motion? To prove at last that Venus is not static but alive, not in the biological sense but in the geological rhythmic sense? For one thing, it would reshape our understanding of rocky worlds everywhere. Most exoplanets discovered near their stars are Venus-like, hot, heavy, clouded, geologically sealed. We have assumed them lifeless because they resemble our image of a dead twin. But if Venus still breathes, then perhaps these others do too. Perhaps geological vitality is not rare but common, a natural outcome of a world's long, slow conversation with heat. It would also deepen our understanding of planetary destiny. Venus and Earth began alike, similar size, similar mass, similar composition, yet one became a cradle for life, the other a crucible. If Venus still moves, then her tragedy is not one of death but of endurance. She continues to fight against her own design, cycling endlessly between creation and destruction. In that sense, catching her motion would not just prove she's alive, it would reveal that she's trying to live in her own way, against impossible odds. Still, there is something humbling in the idea that we may never see her change with our eyes. Even with radar and probes, we are listeners at a door that opens only slightly. Her atmosphere hides, muffles, distorts. Each new measurement is a translation and approximation, a ghost of the real motion beneath. Venus remains both known and unknowable, her breath felt not seen. And yet, that might be enough. To know that beneath those thick clouds lies a world that still shifts, that still exhales, that still remembers movement, that is enough to make her beautiful again. Not just a warning of what Earth could become, but a reminder of what persistence means. Even after fire, after collapse, after ages of silence, something deep within her refuses to stop. One day, when Veritas sends back its first radar sequence, when we compare the images frame against frame, and find a vent that has widened a slope, that has brightened a plume, that has risen, that will be the moment. The moment Venus exhales in front of us. The moment we realize that silence does not mean stillness. The moment we see a planet breathe. And perhaps when that happens, the reflection we glimpse will not just be of Venus, but of ourselves, of our own restless world, turning, moving, transforming in slow time. Two sisters, one green and one gold, still alive after all, still bound by heat, still writing their stories in motion and light. Venus waits. For now, she turns in her shroud of gold, her clouds swirling like smoke around a furnace that will not cool. We have mapped her, measured her, modelled her, but we have not yet heard her. The next decade may change that. For the first time in human history, we stand on the edge of hearing a planet's pulse. The coming missions, Da Vinci Veritas and Europe's Envision, are not just machines of exploration. They are stethoscopes pressed to the chest of a world. Their goal is simple in words, but profound in implication to listen. To measure heat, pressure, chemistry and motion, until the rhythm beneath Venus's silence becomes audible. Every signal will be a heartbeat, every data stream a breath. And in those patterns, we may finally understand whether the planet beside us is dead sleeping or alive in a way we have never seen before. The Da Vinci mission, deep atmosphere, Venus investigation of noble gases, chemistry and imaging will arrive first. It will not orbit safely from afar, it will dive. Through the thick clouds, through the rain of acid, through the pressure that would crush a submarine. Its probe will fall slowly, its instruments sampling the air every kilometre. In that descent, it will read the planet's atmosphere like a diary, the balance of noble gases, the ratio of isotopes, the fingerprints of sulfur and carbon. Those tiny signatures will tell us where Venus's atmosphere came from and how recently it has changed. A higher ratio of lighter isotopes could mean recent volcanic releases. Heavier ones might mark the remnants of ancient outgassing. In those numbers lies a timeline, the history of Venus's breath. By the time Da Vinci reaches the surface, if it survives long enough to transmit, it will have taken the most complete chemical portrait of the planet ever made. Each molecule it detects will whisper of deep processes of gases once trapped in stone, now freed again by hidden fire. At the same time, NASA's Veritas orbiter will circle above its radar, and spectrometers trained on the same regions. Veritas will map the surface with resolution 100 times sharper than Magellan's. Its radar interferometry will measure even the smallest changes in elevation, millimeters of swelling, before an eruption, centimeters of collapse after. If the planet moves, Veritas will see it. If the crust expands or breathes, it will feel the tremor. This is how one listens to a planet, not by sound, but by pattern and change. But Veritas will do more than measure. It will also search for heat signatures, infrared traces of warmth beneath the cloud deck, chemical hot pixels that may betray ongoing volcanic activity. If these regions correspond with the sulfur spikes detected in the upper atmosphere, we will have a chain of evidence connecting gas to vent, vent to plume, plume to mantle. It would be the first complete link from Venus's interior to its sky, a confirmation that her inner fires still speak to the outer world. The European Space Agency's Envision mission will follow, providing the deep echo to Veritas's map. Its radar will penetrate further imaging layers of crust beneath the surface. Where Veritas captures the skin, Envision will see the bone. It will search for buried channels of cooled magma fossil conduits of lava flow, and the deep fractures that feed the coronae, those great ringed scars that may still act as planetary lungs. Together, the missions will weave a full anatomy of Venus body breath and pulse. If all goes as planned by the mid-2030s, we will have more data about Venus than from any other planet except Earth and Mars. We will know her temperature variations by the hour, her gas compositions by the molecule, her surface changes by the centimeter. We will know how her rotation drifts, how her crust flexes, how her atmosphere trembles with thermal tides. It will be as though we are watching a slow-motion heartbeat, one that takes centuries to complete a single contraction. Yet what makes this next chapter extraordinary is not the technology, but the possibility of hearing something unexpected. Perhaps the radar will detect tremors, tiny quakes that ripple through the plains caused by movement in the mantle below. Perhaps the descent probe will find chemical imbalances that can only come from fresh volcanic outgassing. Perhaps one of the orbiters will witness a sudden brightening on the surface, a vent opening a plume, rising a world exhaling after centuries of stillness. Each of these discoveries would rewrite our understanding of Venus. She would no longer be a relic of planetary failure, but a complex organism of stone and heat, a system still active, still cycling. It would also force us to reconsider the definition of habitability. If Venus still breathes, then so might countless other worlds, orbiting distant stars, planets we have dismissed as too hot, too thickly clouded, too lost. Venus would become the archetype not of death, but of endurance. There is something poetic in the timing. We are returning to Venus more than half a century after Magellan's mission ended. A human generation has passed, and so has a geological heartbeat of the planet itself. When we return, the landscape may have changed. If the gradual renewal hypothesis is correct, small flows of lava may already have spread since the last mapping, fresh enough that Veritas will catch their shimmer in radar echoes. It would mean we arrive just in time to see a planet mid-breath. Listening to Venus's heartbeat will not be easy. The data will be noisy, ambiguous, even contradictory. Venus speaks through turbulence, and her language is one of complexity gases, mixed by winds, temperatures distorted by pressure, radar signals refracted through storms. But if we have learned anything from decades of study, it is that meaning hides in the noise. What we call chaos is often rhythm, too slow for us to hear. Perhaps that is what Venus has been all along, a rhythm we have yet to tune into. Her thick clouds are not walls but filters. Her silence is not refusal but patience. For centuries she has endured our misinterpretation, our myths of goddesses and infernos, our simplifications of evil twin. Now we approach not as conquerors, but as listeners. With radar chemistry and light, we are learning her language. And maybe when the first results arrive, they will come not as a roar of discovery, but as a murmur, a subtle pattern in heat, a faint tremor in the data, a small change in brightness where a volcano once stood. That will be enough. A whisper is all we need. For in that whisper lies proof of motion, proof of persistence, proof of life as a process that never truly ends. Venus will not thank us for listening. She does not need to. Her story is older than our species, older than our oceans, older even than Earth's first breath. She has burned, cooled, and burned again countless times before we learned to name her. What matters now is that for the first time we will hear her not in myth, but in truth. And when we do, when the data from Veritas, Da Vinci, and Envision align into a single rhythm, we will know that the planet next door is still speaking to the cosmos, still turning her slow, radiant heart beneath the clouds. Her voice will not be loud. It will not come as thunder or quake. It will come as heat, as chemistry, as motion, too subtle for eyes but perfect for instruments. It will come as the pulse of survival itself. Venus waits patient and bright, wrapped in her eternal dawn, and soon, finally, we will listen.